We'll start with Hugo and his third and final lecture, as well as the others who will be lecturing today. And as usual, if you have a question, just feel free to unmute yourself and ask. Alternatively, you can just put the question in the chat and make sure to address it to everyone so that somebody can respond. All right, so Hugo, do you want to take it away?
Okay, can you hear me well?
Yes.
Yes, perfect. Okay, so just a brief recap of what we are going to do today. So on Wednesday, I justify that once you have analyticity and you have an existence of these analytic families of condensed solutions, so solutions that are already close to kind of the limiting distribution we want to, the limiting measure we want to get, that then we can ensure that the eigenvector and the eigenvalue that are split by the Bethe-Ansatz are indeed the Perron-Frobenius ones, and you can also make the asymptotic expansion. Okay, so what I'm going to do today is explain to you first how you get existence of condensed solutions. Okay, so try to kind of do like yang and yang, but to prove condensed solution at the same time, that the solutions are condensed. And then I will explain to you how you get analyticity. Unfortunately, you will see there is a small assumption, and I will comment on that. Okay, and if time permit, I will explain how you do the expansion of the Fn capital N and not F capital N. But this is not completely clear. So just a brief recap. So what I'm going to do, because actually that's the most interesting case. I mean, that's the hardest case. So I'm going to restrict myself to delta, sorry, I'm still with my wrong, from delta between -1 and 0, okay? I will comment a little bit on the delta larger than 0. The delta smaller than -1 works really a little bit differently, but it's still simpler in some sense. So I don't want to be commenting it. So just a recap, we had a Bethe equation, which I will call BE like that, which is the following thing. We want to look at lambda i's that satisfies the following thing for j equal 1 to n equal 2 pi I over n, and this guy here is I minus n plus 1 over 2. Okay, so this is a set of equations. We want them for I equal 1 to n. So we are looking for the lambda I. I commented on Wednesday that there is a continuum or continuous, I don't know, Bethe equation, which is going to be denoted like that, which is kind of a limiting version of, I mean, it's describing the limiting distribution, the limiting point measure of the lambda I. So it's going to look like that. It's going to be the integral between minus q and q of k of lambda minus mu, rho of mu q d mu equal psi of lambda. And here I want to be telling you, I didn't do it on Wednesday, but just let me give you the formula for p, theta, psi, and k. Not really that you are going to be able to read them, but at least I just want to make it very clear that they are extremely explicit. So one is this one. I zeta, this is a zeta, sorry. I zeta over 2 and I zeta over 2 minus x. This is p. Theta is almost the same except that you put zeta instead of zeta over 2. Remember, zeta is arc-cosh of delta. And psi and k, maybe let me not give the formula, but let's remember it's p prime divided by 2 pi and theta prime divided by 2 pi, okay? And then, I mean, if you like it, you can yourself compute the formula for these guys. Okay, so what are the two theorems I'm interested in? The first theorem was a theorem that I called 7, which is existence of condensed solutions. And this compared to existing theorems, the advantage is that, I mean, existing theorems were proving the existence of solution, but they were not necessarily condensed. So there was some work to try to prove they are condensed. Here I'm going to explain to you that if you do you take the problem by the right side, in fact, condensation comes for free, basically. So the theorem is going to say the following: if you take n smaller or equal to capital N over 2, then there exists, and remember that we are in this regime, huh? I'm not going to repeat it. Then there exists a lambda, which is lambda 1, lambda n, such that, well, lambda is solution to the Bethe equation. Okay, we are looking at solutions. Lambda is symmetric. So remember, symmetric meant that this is minus lambda I, and or strictly order, I'm going to even say. So this means lambda I strictly smaller than lambda I plus 1. So this, by the way, is really, you want this. I mean, these two things are very convenient things to have. But the interesting property is the property of condensation, which is that for any function f from R to R, which is with integrable derivative, you have the following property that, sorry, okay, maybe let's, that 1 over capital N sum of the f of lambda I, in fact, is very close to the integral between minus q and q of f of lambda rho of lambda q d lambda. And by very close here, I mean smaller than a constant that depends only on delta, and I will tell you what it is, divided by capital N times f prime of L1 of R. And here, I just need to tell you, you see here, the Q was referring to the choice of this Q here. So I need to tell you what Q here is, and Q is a function of N over N, and in fact is such that the integral between minus Q and Q of rho of lambda Q d lambda is small n over capital N. By the way, it's not entirely clear that this is a well-defined Q, that you can always find such a Q, but the analysis of this continuum Bethe equation is really not that hard. So, I mean, this is by basic analysis, you can prove in particular that there always exists such a Q and such a rho lambda Q. Okay, so it's not, the difficulty doesn't come from trying to get information on this quantity. This quantity is, think of it as very simple to compute. Okay, so the trick here, the important part is really the existence of this lambda that has these properties. Okay, so this is I mean, yeah. Okay, that's the first theorem, and the second theorem is the existence of analytic families, because we saw at the end of last class that at least it simplifies quite a lot the study. Maybe you can go around it, but I don't know how, but with analyticity, it's fine. And there I would say that for any delta 0 between -1 and 0, there exists a k, okay, which is a k of delta 0, such that there is an analytic family delta gives lambda of delta defined on delta 0, 0. Okay? That's the second thing. So the more you get close to -1, the more you need to increase the k here. So you, oh, sorry, the k for every n smaller or equal to capital N over 2 minus k. Sorry, that's the constraint. Okay, so the more you try to get close to delta to -1, the more you need to remove the largest possible values of n. Okay, we don't believe this is necessary, but at least the technique only gives that. And by the way, if you want to go up to -1, then it seems, I need to check, but it seems that you can take delta 0, I mean k to be log n, log capital N, and then you have a full family defined up to -1. Okay, so let's start with the first theorem. So proof of theorem 7, the existence theorem. And maybe I'm going to just copy paste it. Let me copy paste it, that we have it here. So it's the existence thing. And the idea, well, the idea is not new and it's actually quite natural. I think it will surprise absolutely nobody, is to try to use a fixed point theorem, okay? So what we are going to do is we are going to use Brewer fixed point theorem. So by the way, you are going to see the proofs are very simple, but I mean, it took us some time to actually get it in the right form. So now the proofs are simple, but at the beginning they weren't. So use Brewer fixed point theorem, apply to a certain map. And in this map, there is going to be, the trick is going to be to look at the right space on which you want to apply it, the omega. But for now, let's ignore that. And this map is mapping lambda to mu, where you define mu I as follows. P of mu I must be equal to 2 pi I over n plus 1 over n sum for j equal 1 to n of theta of lambda I minus lambda j. So you notice that if you have a fixed point, if this guy here is lambda I, this is exactly the Bethe equation, okay? So if I find a fixed point, I'm automatically getting a solution, okay? Also notice that the solution, in fact, is automatically ordered and symmetric if the lambdas are ordered and symmetric. So if lambdas are ordered and symmetric, then mu also is. So really what we want to prove is be able to apply the theorem. So we need to map omega to itself. We need to choose the right omega. We could take Rn, well, it's not a compact set, but we can try to take like a very big set. It's going to be much simpler to prove that it's mapped to itself, but it's going to give less information on the solution. And this is going to be problematic to try to prove the last property, which would be that mu, I mean, that the fixed point is necessarily condensed. Okay, that's going to be the trick to try to find that. So at this stage, I just want you to remember that a fixed point is the solution to Bethe ansatz. Okay, so what is going to be the trick? Let's try to find what is the right omega. So the trick is very, I think, cute and quite simple, is to try to apply, I mean, to try to look for solutions that are interlaced with the quantiles of the distribution rho tq dt. So what do I mean by that? So let's define the following. Let's say that lambda is k interlaced. Okay? If for every I between 1 and n, you have that lambda I minus k is smaller than lambda I, smaller than lambda I plus k, where lambda is defined as follows. The integral from 0 to lambda x of rho of tq dt is exactly equal to x minus n plus 1 over 2 divided by n for q, which is still the q. I mean, from now on, we will always look at this q. So let's not bother too much. Okay, so if you would have to guess and you expect to have condensation, let me go back a little bit. If you expect condensation here, it's kind of not so surprising to expect that the lambda I are roughly going to be close to exactly the quantity which, when you integrate from 0 to it, you end up with II. Okay, so you kind of expect that this thing is roughly, I mean, of rho of TQ dt is roughly II over N. Why? Because if you think about it, the integral from 0 to lambda x of rho of TQ dt, in fact, this is very easily expressible in terms of, I mean, this you can get by integrating the continuum Bethe ansatz. So by integrating the continuous Bethe equation, one gets almost what you get from the Bethe equation. So you get the integral from minus q to q of theta of x minus lambda rho of lambda q d lambda plus, so how did I write it? Sorry, you get it px minus the integral between minus q and q of theta of x minus lambda rho lambda q d lambda. But if you have condensation, you really expect that this is almost like the sum of the theta of lambda I minus lambda j. So if you apply here, and there is no x here, it's just integral from 0 to x. So if here you plug lambda I, you expect lambda I here, and this should be like the sum of the theta of lambda I minus lambda j. So you expect that this should roughly be like II over N. Okay? So the problem is that this is if you assume condensation. But because we are going to use a fixed point theorem in some sense, we can kind of do it for now. Wishful thinking, but let's do it for now. And then it's kind of natural to expect lambda I is going to be close to this capital lambda of I in some sense. So in order to say how much you are close to this capital lambda of I, you compare it to lambda to capital lambda of I minus k and capital lambda of I plus k. Okay, so this is what we call a k interlace solution, a k interlace vector. And the good property about k interlace things is that lemma, which I'm going to call from interlacement to condensation, is that if you start, on the other hand, with an interlace solution, then you get condensation for free. So what I claim is that for every k interlace solution, and for every f with integral derivative, I have the following. If I compare that to the integral, I end up with something quite quantitative, actually. I end up with 2k over n times the L1 norm of the derivative. Let me put this in red. And I'm going to prove it to you in a second. It's a very simple thing. I even planned at the beginning not to prove it, but I think that maybe it's better if I give the right thing. Okay? And furthermore, in fact, because this is going to be important, furthermore, is f is monotonic, then you can replace 2k by k plus 1/2. Okay? I'm going to tell you why in a second. So if by chance I would be able to prove the existence of k interlace solutions, then I would get condensation for free with a certain constant, which is expressed in terms of k. The bigger the k, the worse the constant in the quantitative interlacement. Okay, so let me prove to you this lemma because it's an absolutely straightforward thing to prove. So we were at page 20. So what we are going to do let's start with f arbitrary. So let's look at this. And let's use that the integral of rho of lambda q d lambda between lambda j minus 1/2 and lambda j plus 1/2 is exactly 1/n. So this here is therefore smaller than this quantity. Right? So I'm just kind of transforming the second sum, the integral into a sum, and then I get this. But now, notice that it's straightforward that f of lambda j minus f of lambda is smaller or equal to the integral, I mean, is actually equal, but I mean, smaller or equal to the integral between lambda and lambda j of f prime of mu d mu. But because lambda and lambda j are between lambda j minus k and lambda j plus k, I end up with this trivial bound. So here, I use that the lambda j is between lambda j plus k and lambda j minus k. Okay? Maybe I also use that k is larger than 1/2, but here actually, if you think about it, you really are interested in this case. Okay, so then when you replug this here, you end up immediately with the fact that this is smaller than the sum for j equal 1 to small n of the integral between lambda j minus k and lambda j plus k of f prime of mu d mu. And this, if you think about it, it's exactly smaller than 2k. I mean, oh, sorry, and there is a 1/n here that I lost. And I get 2/n times f prime. This is really something that anybody can do on his own, okay?
If I wanted to give it by equations, I can give it by equations.
Rick, we hear you. I don't know if it's intended. I don't hear you well. Ah, okay. Okay, so this is a proof for f arbitrary. If f is say, increasing, then you kind of play the same game, except maybe instead of using this kind of bound, you use something slightly smarter, which is bounding by lambda j plus k, lambda j plus k plus 1 of f of lambda rho of lambda q d lambda. And here it's divided by n. And here you do the same with j minus k minus 1 and lambda j minus k. And then you sum. So you see that you can only sum, say if you want the upper bound, then you sum for j from 1 to n minus k minus 1/2. And then you need to bound the k minus 1/2 remaining terms. And you need to bound from below the integral. So let me maybe write it because I mean, this is the type of thing. So then the sum is smaller than the integral between minus q and q, except that we still have the sum from j strictly larger than n minus k minus 1/2 of f of lambda j over n. And in fact, if you think about it, we have the integral from minus q to lambda k plus 1 that we also need to put. So we have something like that. And then this guy, oh, what did I do? Oh, this is, sorry about that. Okay, this guy you bound by f of plus infinity, and this guy you bound by f of minus infinity by monotonicity, and you end up exactly with the right term, meaning this plus k plus 1/2 of f prime L1 of R. Okay, so it's my point was to really convince you that this is a very simple argument. There is nothing super fancy behind all of that. Well, once we have this notion of k-interlacement, you are going to see the proof is absolutely straightforward. Why? Because what we do, so recall that, so proof of theorem 7. So recall that P of mu I is 2 pi over n plus the sum from j equal 1 to n of theta of lambda I minus lambda j. Okay. So let's define omega kr to be the set of lambdas which are symmetric, ordered, k-interlace, and such that the lambda I are smaller than r. This is just a technical thing. We want to apply Brouwer theorem, so we need to be on a compact set. Okay. And then what you notice is that first thing, one can pick r equal r of n such that you are certain that the mu I are smaller than r of n, even in fact if the lambda I aren't. And this is just due to the fact that the right-hand side here, if you think about it, this right-hand side is smaller or equal to pi minus zeta minus 1 over 4n or something like that. It's just something which is easy to get from bound on theta and from the fact that I is I minus, I is I minus n plus 1 over 2. But if it's like that, P is actually mapping R into minus, so P was mapping R into plus minus pi minus zeta. The interval minus pi over zeta and pi minus zeta. So it's clear that you can define R of n sufficiently large that you are certain your guys are in this interval. Also notice that omega k R is clearly a convex set. So really, the only thing we need to check is that if you take lambda in this guy, so that means that lambda is k-interlace, we need to check that mu also is. Okay? So let's try this. And in order to do that, what we are going to do is let's look at P of mu I. I multiply it by n just for convenience. And let's notice that this is smaller or equal. So if I take this thing here, so it's equal to the fact where I put this thing over n, and here I put the sum. But if I replace the sum by the integral, and there is not over n anymore, if I replace the sum by the integral, mu I minus lambda rho of lambda q d lambda, I'm making a mistake. But this mistake, because lambda is k-interlace, is smaller than k plus 1/2 times the L1 norm of theta prime. Okay, which by the way is a monotonic function. So this is just theta of plus infinity minus theta of minus infinity. And by what I just said, it's 2 pi minus 2 zeta. Okay? Okay, by the way, I probably just made a mistake. It should be 4 zeta. So here it's 4 zeta. So maybe here I just forgot a 2 here and a 2 here. Okay? Okay. But now let's imagine that I choose K. So this is going to be the trick. Choose K so that K plus 1/2 times 2 pi minus 4 zeta is strictly smaller than 2 pi k. Okay, I can always do that. It gives me a certain k, and by the way, because when delta tends to -1, zeta tends to 0, you end up with a worse and worse k when you get closer and closer to -1. So -1 is really the place where things get messed up, okay? But if you choose this k, then you end up that np of mu I is strictly smaller than 2 pi I plus 2 pi k plus the integral between -q and q of theta of, sorry, this is lambda I. It's not mu I, it's lambda I. It's this guy. Theta of lambda I minus lambda, rho of lambda q d lambda. But here again, by monotonicity, I can replace this by I plus k because I'm k interlace. Why do I want to do that? Because what do I recognize here? I recognize 2 pi I plus k plus the integral between -q and q of theta of lambda I plus k minus lambda rho of lambda q d lambda. And this, by the way, was exactly what I defined to be P of lambda I plus k. So this is due to this formula that I mentioned somewhere here. If you apply here this formula to capital lambda I plus k, you exactly end up, by definition of the lambda I plus k, on 2 pi I plus k plus this integral. So I get P of lambda I plus k, and therefore I get that mu I is smaller than lambda I plus k simply because P is strictly increasing. So here I used theta is strictly increasing. Sorry, I should have said it. But these are two properties that are extremely simple to check. It's basically saying that k and psi are positive, which is straightforward to check in this regime. Okay, and then you do the same for mu I larger than lambda I minus k. And then you use, so that means that omega k plus r, kr is mapped into itself. And therefore, by Brewer fixed point theorem, one gets the solution in, the fixed point, and therefore a solution in omega kr. Okay, so it is, to my opinion, it's a very, very simple proof. Once you see it, it's very simple, and I do think it's simpler than what is in the literature usually. But of course, it's difficult to run through all this literature, so maybe this argument even appeared somewhere. I'm not, but I didn't see. So we have existence of condensed solutions. Let's now try to prove that there exist analytic families of solutions. Existence of analytic families, the family of solutions. And that's where things get a little bit worse. By the way, if you are interested, because I'm pretty sure some people are, in the case where, okay, maybe just a remark before I do that, I dive there. Just a remark, because I know people are interested in the case delta equal 1 here quite a lot. So maybe people may be interested in delta between 0 and 1, even though it's not what you look for. But for instance, if you want a simple argument to prove existence, to compute the free energy of square ice, just one remark, which is that when delta is between 1 and -1, between 0 and 1, then you need to be a little bit careful because theta becomes decreasing here. So in this case, you need to actually define psi of, mu by the following. You need P of mu I minus sum, 1 over n sum of theta of mu I minus lambda j equal to pi I. Okay, so it just, before here, we had lambda I. Now you put mu I itself in it, and then you have all the properties you want. Things works perfectly, and you still have this, this fixed point theorem. Okay, That's just a remark. Okay, so let's now try to prove existence of analytic family of solutions. So let's try to prove theorem 8. In order to prove this theorem, we are going to introduce the following map, T delta of lambda, which is defined, so it's a vector, okay? And T delta of lambda I is just 1 over 2 pi P of lambda I minus 1 over 2 pi n, sum for j equal 1 to n of theta of lambda I minus lambda j minus II over n, okay? And there you will agree with me, it's not science fiction, that the zeros of T delta of lambda are solutions to the Bethe equation. Okay, so our goal is to prove that you have a continuous family, an analytic family of zeros for this map. Okay, so let's make an assumption first. Let's make the assumption that T d delta of lambda is invertible at a certain delta 0. So you have a lambda, which is solution to the Bethe equation at delta 0, and you assume that dt of lambda is invertible. So then you know that the implicit function theorem implies the existence of a continuous, of an analytic, family of zeros. It's easy to check that you can restrict yourself in such a way that this thing is going to be ordered and symmetric. Okay, so you can add symmetry and order. Okay, so what the implicit theorem tells you that on a small interval, you get an analytic family of solutions. But what you would like to do is to go from local to global and to create by connexity a big family. So if it was true that whatever the lambda, the thing is invertible, it will not be difficult to create a full family. We are going to see we don't know how to prove that, at least in general. So we are going to ask here that lambda is also condensed. This is going to be used to try to prove that dt is indeed invertible. Okay? So what we would like, ideally, is that the condensation property keeps going. It's still true. If it's true at lambda 0, it's true a little bit away from lambda 0. Okay? But the good thing is that if instead of condensation, we ask K interlacement, if lambda is K interlace, then in fact, one can prove that lambda of delta is K interlace for neighboring delta. So why is it true? It's true because if you are symmetric ordered and K interlaced, in fact, what we just proved before is that you are strictly interlaced. If you start from a lambda, which is K interlace, and you apply the map, and if it's a solution, in fact, it's a fixed point of the map, so you can apply it and refall on yourself, but then you are strictly interlaced. And if you are strictly interlaced, then you remain strictly interlaced for a small interval because everything moves continuously. Okay? So in fact, here, if you start with strict interlacement, you end up with a family of strict interlace lambdas around you. And by the way, it was the same trick with ordering. If you want to guarantee ordering, what you can check is that, in fact, if you are ordered, then you are strictly ordered, necessarily. If you are a solution which is ordered, you are strictly ordered. So you define this as being open properties, and you are certain that it doesn't cease to be true on a whole small interval. So now it's good because what you can do is you can think by connexity. Because what you also know is that if you have a family of k-interlaced solutions, which are symmetric and ordered, then the limiting point and converging to a certain lambda of delta zero, this lambda of delta zero is in fact not only interlaced, symmetric and ordered, but it's also strictly interlaced, symmetric and strictly ordered. And then you can apply again the thing. So just here, a connexity argument allows to go from local to global. So everything is perfect. The only thing we need to check is that if lambda is k-interlaced, and maybe a solution to better on that, but this is actually not even really necessary. I mean, we didn't know how to use it. Then dt of lambda is invertible. That's the thing we really need to check because that was our assumption here. We really need to be using the implicit function theorem to prove that they are analytic families. Okay? So what I'm going to try to explain in the last slide, I mean, it's not quite the last slide, but almost the last slide, is why dt is indeed invertible, at least in the range of parameters that we are interested in. Okay, so dt at a certain ij, I mean, you can check from the formula of t here that dt is in fact psi of lambda I minus 1 over n sum from j equal 1 to n of k of lambda I minus lambda j. And it's k of lambda I minus lambda j over n. So this is if I equal j, and this is if I is not equal to j. Okay, this is just a simple formula for the differential. And the first remark is that if you are between 1 and 0, there things are perfect. Why? Because when you are between k and 0, k is smaller or equal to 0, and dt delta of lambda is definite positive. So in fact, you can even define an integrated a primitive of t delta, which is going to be a convex function. So there, of course, dt is invertible, and also, in fact, there is a unique minima, and there is a unique solution to better on that. So the delta between 0 and 1 is by far the simplest regime. Okay. Okay, so now let's try, so we are not between 0 and 1, so let's try to see what we do. So the idea is going to be to define the following matrix. And there, by the way, there may be other ways of proving that it's that dt of lambda is invertible. We didn't find one, but I'm definitely not claiming there is not other ways, but I think we found a cute one, which is to transform the matrix a little bit by dividing by rho of lambda j q, and to prove that A is diagonal dominant. And if you have a diagonal dominant matrix, then it's invertible. Okay, and you are going to see this matrix actually hidden behind it. The coefficients are very simple in some sense. So to try to convey the idea that it's quite simple, let's look at AJJ. the diagonal term. So this is 1 over rho of lambda jq. And then you have this psi of lambda j minus the sum. But remember that here we are looking, we are assuming that lambda is k interlace. So if lambda is k interlace, I can actually transform the sum into an integral. Of course, I'm making a mistake when I do that. Let's put it in green, which is this thing. Right? Okay. So there, what is good is that this thing here, well, by the continuum Bethe equation, it's equal to what? Well, it's exactly equal to that. So this thing is in fact 1 minus 2k k prime over n rho of lambda jq. Okay, so it's not so bad because maybe we can expect that this remainder term is small and therefore we get that the diagonal term is roughly 1. So let's now sum the akj for k not equal to j. So in this case, this is the sum for k not equal to j of k of lambda j minus lambda k over n rho of lambda j q. And this thing, lambda k q, sorry. So maybe you want to sum the jk. And this, again, we can play the same game of replacing by an integral of k of lambda j minus lambda over rho of lambda q d lambda, where there I use the condensation assumption, but for the function k of lambda j minus dot over rho of dot q, and I get a prime when I'm looking at the error term. So why is it good, this? Because the red term is the integral of k. And the integral of k is simply theta. So this is just theta at lambda j minus q minus theta at lambda j plus q. And sorry, because there is a minus in the thing, you actually get this. So this is smaller or equal. Remember that theta is going between minus pi plus 2 zeta and pi minus 2 zeta. So this is smaller than 2 pi, and I lost a 2 pi somewhere. Oh, here I lost a 2 pi. So this was 2 pi. So I get 2 pi minus 2 zeta, 4 zeta. So it's perfect because you see here you get a 2 pi. And here you get a 2 pi minus 4 zeta. So if you forget the error terms, you indeed have a diagonal dominant matrix. The only thing that you need to be very, very careful about the order of magnitude of these errors. So trust me that they are of the same order of magnitude. This is roughly the same as this. So let's look at 2k, k prime over n rho of lambda j q. So the top term, this term here, it's of order 1. It's neither small, neither big. It's something, it's like, depends on k. So it gets worse and worse when k gets bigger, but otherwise it's not very nasty. The problem comes from this guy. This guy here is actually quite big. Rho of lambda jq is quite small when j is close to 1 or 2 capital N, to small n. So very small when j close to 1 or small n. And that's why people in the past, they didn't do it like that anyway, but the theorems they were getting were from small n over capital N, which is away from 1/2. Why? Because in this case, this rho of lambda JQ is in fact bounded away from below. It's not small. So if it's not small, the error term is roughly big O of 1 over capital N. Okay? The problem is that here we want to kind of have something more quantitative and to reach values that are very close to capital N over 2. And then, in fact, there, if you take, so when N is smaller than capital N over 2 minus, 1 minus alpha, you get that this guy is larger than epsilon of alpha. But if you take capital N over 2, rho of lambda 1q is in fact 1 over n, roughly. So this is catastrophic because it tells you that the error term is actually quite big. And this is something we discussed it with Carol. It's something very, I think that in all computations at la Baxter and Lieb, and this was ignored. The problem of what happens on the boundary, how this lambda j on the boundary behave, this seems to be quite interesting, and we didn't really see any treatment of that. So Carol was not really able to tell us full description of what happens on the boundary. So the best thing we came up with is that if you take n, which is capital N over 2 minus k, in fact, even on the boundary, it's kind of easy to see that this is like 1 over k times n. K over n, sorry. So where k is this k, right? So this k here is this k here. So that means that 1 over this is in 1 over capital K. And there you can take capital K large enough that this error term is smaller than, say, 2 zeta strictly. And if this guy is also bounded by 2 zeta, which you have to believe me, but you can do the same analysis for this guy, and it boils down exactly to the same quantity, then you end up with a diagonal dominant matrix. Okay? So this is the end of the proof. Just I didn't explain to you how you do the row analysis, but this is really analysis in the continuum, and it's very elementary one. Let me make a comment here. That there is a paper by Mike Coy and a co-author that tells you the following. If you take the Perron-Frobenius eigenvector, psi of delta, in fact, when you look at its norm, it's L2 norm, I think, if I remember, it's a certain function of the lambda, which is extremely explicit, very explicit. Let me put off lambda here. So this guy, nothing is hidden there. It's very explicit. It's non-zero. But what you get after that is that of dt delta of lambda. So you see, indeed, I mean, if you want to use the better equation, and the better on that to give you the Perron-Frobenius eigenvector or any eigenvector, I mean, it must be that the vector that it's giving you is non-zero. If it's 0, it will give you 0 information. And what I'm saying is that the fact that it's non-zero is directly related to the determinant of this, this equation, the determinant of this differential. So there is really like, it's two sides of the same problem. That's, I think it's kind of interesting to know. Actually, I have some remaining time, so maybe I'm going to just sketch to you very briefly how we prove the last theorem. So this is 3.4 maybe, and it's a proof of the theorem which was the asymptotic of this guy. And if you think about it, with all the theorems on the better ansatz we proved, in fact, the only thing we need to do here is to estimate. We need to estimate the integral between minus q So remember Q, well, the integral between minus Q delta of small n over capital N and Q delta of small n over capital N of log of L of e to the I P of x times rho of xq dx. It's exactly, we need to estimate that. And maybe, yeah, we need to estimate that. So let's try to do it. And notice that at this stage, it has nothing to do with the discrete better ansatz anymore. So everything I did allows you to bring back the asymptotic of f capital N small n to the computation of the, to the asymptotic of this integral. And I want just to tell you how to run the asymptotic, because this is something that in our first run was 50 pages of computation using this, using Riemann-Hilbert problems and so on, before we just saw a way of doing it in one page. So I wanted to just present this way because maybe it can be inspiring in another problem for you guys. So, okay. Okay, so first thing, because it's just more classical, but instead of looking at this guy, people look at C of x, which is 1/2 of log of L of e to the I P of x, L of e to the minus I P of x. Just because rho is symmetric, so you can just transform it like that. And just, I'm going to use this notation because that's the standard one. Okay. So what we want to be computing, let's call it d delta f of q. Delta f of q is going to be, so another thing, by the way, we are going to do an asymptotic in q. Okay, so step 0. So step 0 is that, in fact, 1 minus 2 small n over capital N, which was the asymptotic we were using in our argument. This is, in fact, like constant over delta plus little of 1 times e to the minus pi q over zeta. Okay? This is also something you can just get easily in the continuum. So the, where this q is q delta of small n over capital N, but I'm going to use this notation because otherwise it's going to be very heavy. Okay? So I'm going to do an asymptotic in q, not in small n over capital N, but think q tends to infinity is equivalent to small n over capital N close to 1/2. Okay? Which is the guy that gives you the free energy. Okay, so that's the first step, and I'm not going to detail it. You have to trust me, it's not very exciting. So this is not it's easy from continuum better equation. Okay, so let's look now at the next step. So the next step is that it's actually much more convenient to rephrase. You see, when q tends to infinity, you end up with an equation. So if I rewrite let me rewrite the better equation just for the pleasure of writing it. So this is the equation in q. And when you take q equal plus infinity, you end up with this one. And this one we said that this is one equation, this is an equation which is very easy to solve. It's an equation which is really easy to solve in Fourier. If you take the Fourier transform, it becomes multiplicative because it's a convolution, and you end up with rho of x, which is simply 1 over 2 zeta cosh of pi x over zeta. So what we would like to understand is why, when q is very large, this equation here, so this is q finite, why this equation is close to the limiting equation. And you can do by hand, and you are going to get results that are not so, it's not as precise as you would like. So let me give you the way of rewriting the equation to really see the right order of magnitude of the, to have the right precision on how close rho of xq is to rho of x. And the trick is to use the resolvent of the Bethe equation, which is just defined by the Fourier transform of R is equal to the Fourier transform of K divided by 1 plus the Fourier transform of K. And if you plug this, like if you start from this equation, and you go to Fourier, you divide by 1 plus k hat, and you go back to space variables, what you end up with is with an equation which, to our opinion, is much more transparent, and which is saying the following. Saying that rho q is satisfying this equation. So you see, it's very good because there you kind of see then when q tends to infinity, the interval of definition of the integral goes to 0, and it seems to be much more reasonable than rho of xq converges to rho of x. And in fact, there you can even really deduce a sharp asymptotic. So rho of xq, you can prove that it's equal to rho of x plus e to the minus q pi over zeta. And this is this pi over zeta, which is not that obvious to make appear when you look directly at this form, at the yellow form here of the equation. But if you rewrite it with this kind of modified continuous Bethe equation, then it's obvious, and you can get something that looks like that, where this is a T is a solution to a half-line equation, which I forgot to write, but maybe let me ignore. Solution to a half-line integrable equation. So something like a T of x plus the integral from 0 to infinity of something is equal to something. Okay? And here it's, you get r of x minus y, t of y dy. And I don't remember what psi 1 is equal to. Okay? But this is not that important. And the important thing here is that this delta t of x is actually a big O, let's call it q. It's a big O of e to the minus 2q. So this is an error term. So you can really make an expansion of rho of xq in terms of rho of x. In particular, you have ideas of how, so remember this is, by the way, remember 1 over 2 zeta cosh of pi x over zeta. So this is going to be our step, I guess, step 1. We have an asymptotic for rho of xq. And then, so step 2, which is the last step, becomes very easy. So you look at delta f of q. So this is the integral over r of c of x rho of x dx minus, so this, I just want, sorry, what did I do here? I didn't define delta. Okay, so now I want to define delta f of q to be the infinite q guy, which is the free energy, minus the integral from minus q to q of c of x rho of xq dx. So this is what I really want to be. I want to get the asymptotic of this guy, but I know somehow, I'm guessing that the first order is the free energy here. So I'm already subtracting it. And here, if you go to Fourier, you end up very easily with the fact that if g hat is c hat divided by 1 plus k hat, you end up with delta f of q, which is an integral over r of g hat of t rho q hat of t dt minus, and here, in order to make sense, well, it's not so important, but you are going to, let me put here, you are going to integrate on delta positive, something like that. So you have two integrals, one on r and one on the shifted version of r. And you are going to have rho hat of t e to the I t minus sq minus e to the minus I t minus sq over t minus s. And you are going to have a rho hat qs and a ds dt. So this, I'm pretty sure that many people in the audience are much more comfortable with this type of manipulations. This is coming from the Fourier transform of indicator. I mean, it's not really defined, but indicator of R minus QQ somehow. It's kind of a version of this. Of course, which is not defined, but. And here, then, the only thing you do is you do a residue computation. You do a first residue computation where you notice that the first residue of G, so there is going to be a residue at, when you integrate in T at S, and there is going to be a residue due to the G, and the first residue is at I pi over zeta, and the second one is at I 3 pi over zeta. And of course, they are symmetric ones. So when you start doing a contour, you deform your integral and get something that looks like that, you are going to see, I mean, this you need to deform in one direction, this in another one, whatever. What you end up with after this careful analysis is that you get minus 2i sine theta over pi e to the minus q pi over zeta. And this thing here is going to be the residue of G hat at I pi over zeta. So the sine theta is encapsulated in the residue of C of this G hat, which is basically the residue of C hat. Okay? And then you are going to end up with the integral over R. That's not going to work. I'm almost done. The integral over R of rho of x plus q e to the minus x pi over zeta dx. And then by step one, this rho of x q plus q, when you plug x plus q in, when you plug x plus q here, you end up with here rho of x plus q, which you can easily expand. And here, t of 2q plus something, which is very tiny. And here, t of x, but there is an additional e to the minus q pi over zeta in front. So this guy here is again of order e to the minus pi q pi over zeta times a certain constant of delta, and all the other terms are smaller. So you end up with 2 powers of q pi over zeta, and remind yourself that 1 power is corresponding to 1 minus 2n over capital N, and that's where the square comes from. This was a very brief thing to finish kind of the whole story, and because I wanted because we all missed it in the group, this rewriting, this modified continuum beta equation is is more tractable. We were really doing things, and there is even in the literature results that are using more complicated ways to get to asymptotic expansion of this type of solutions, while you can just rewrite it like that. So it's a simple observation, but maybe it can be a useful one, and I wanted to tell you about it. So overall, I'm done basically with the lectures. So I know it was maybe a little bit technical, but I thought that, we all heard a lot about the beta ansatz, and we all kind of knew that there are places where maybe it's not completely kosher. In some cases it is, in some others it's not, and which case is what is which, in which category you are at a given time is kind of not always obvious. So I thought I would give you this overview of a very personal and amateur view at it, but we took some time, but I think we found fairly easy proofs at the end of these different facts. And there is this kind of still elephant in the room, which would be to manage to actually get capital N over 2 for delta between 0 and 1. And this is not completely irrelevant, because the behavior of the beta roots at the boundary, so meaning lambda 1, lambda 2, or lambda n minus 1, and so on, they contain in it information on critical exponents. So it's not at all a stupid question, and it will be very interesting to have a cleverer argument than what we got to manage to go further in the study of these boundary beta roots. Okay, so thank you very much, and thank you for your patience also.
Okay, well, thank you very much, Hugo. We have time for questions, and maybe I'll start with one question, which is just, could you maybe put references for those things that have been done? I know you had to work a few years ago, kind of an expository piece, yeah. But is the stuff you talked about today?
So yeah, I mean, unfortunately, the thing I talk about is, I mean, it's written, but we are polishing it. So it's a little bit a problem. It's going to be on the archive by the end of the month, I think. I mean, not this month,
sure.
August. Because I mean, we got proof in very simple cases, and then we realized we can make things quantitative and they are not completely uninteresting. So that's why we are kind of always rewriting it. You can talk about it with Dima Kratchun, who wants to kill me. So at least confinement allows me to survive until he comes back to Geneva, because every week I'm asking that we do it differently to improve a little bit the exposition. So I hope to be able to put this paper on the archive soon. On the beta ansatz itself, we had this argument, we had an expository thing, but really just for, I mean, how you get the formulas and things like that. But I'm a little bit ashamed of this thing. Maybe it's not, I mean, for people like you guys who know much more than me, maybe we don't do it in the right way. We do it in a cute way, but is it the right way to understand the beta ansatz? I'm not certain. So I'm not sure I would recommend the reading so much, but you can look at it indeed. It's a paper with, so myself, there is Manulescu, there is Matan Harel. So this is not alphabetical order, but I mean, and Tassion, and it's something like beta ansatz for dummies. No, it's not called like that, but it should be called like that probably. And then there was this.
Looks similar, so it's almost alphabetical order.
Yes, it is. And maybe there is there is also another person who left academia. So when you leave academia, you get removed. So, but so there are two papers actually. There is this beta ansatz exposition. And there is also the paper where we prove that for Q larger than 4, you have a discontinuous phase transition for a Potts model. Because before the analytic, I mean, the beta ansatz type computations were actually using 8-vertex model and things like that, where there, we don't still, I mean, I still don't know how to justify fully what happens there. So we found another way to use beta ansatz to prove this discontinuity. Now the beta part, I mean, really the study of the beta ansatz in this paper, I think is really superseded by what we do in this new paper that will soon arrive, which I really think we do it in a better fashion. So soon, I mean, I mean, if you are, what I can suggest is that if you are interested in having a look at this paper and that you are afraid you are going to not see it on the archive when it gets out, you send me an email, and every person that sends me an email, I promise I will send you the paper as soon as it's finished. Okay. Otherwise, you can check archive, and I'm not going to hide it from you guys for long. So normally, it should be available soon.
Also, what when delta is bigger than 1, do the techniques extend to showing?
I didn't look at it at all for delta larger than 1. I cannot tell you on top of my mind what. So here, I mean, we do this asymptotic analysis when around n over, I mean, capital N over 2, which I mean, to get delta larger than 1, you will need to take the asymmetric model, and there it becomes unclear, right? Which is maximizer. So I don't know if we could ask even the same question. So probably maybe justification of the existence of, I mean, all the Bethe equation theorems, they may work very well. I don't know. I need to check that. But then the asymptotic of this F capital N, that I would not know how to do near the maximizer, at least not naively.
Other questions for Hugo?
I'm curious. I have a not very well defined question. I'm sure you looked at the physics literature, at least at times, to see what they say about these things.
Yeah.
Is there a general feeling that they basically knew what's going on, but didn't care to work out the details, or there is a feeling that there was some gaps that they didn't care about and just pushed forward?
I mean, it's a tricky question.
I know, I'm not going to quote you on the answer, I promise. But.
So I know that, for instance, I remember vividly a discussion with Elliot, where he first told me that what he did in 67 was rigorous. And then later on, he had this he came back to me with the fact, oh, one of my students made it rigorous in 2004, Goldbaum.
Okay.
So, I mean, in some sense, you have this double, let's say, speech. I know that Karol Kozlowski really, I think, know his stuff on Bethe-Ansatz. And there are recent results that really, I mean, very recent, like 2017, proving condensation when small n over capital N is away from 1/2. So really kind of a baby version of what, and the proof are not that simple because so I would be tempted to say that maybe some people knew, and definitely, I mean, I'm not claiming that we made a huge discovery. I mean, I think many of you, if you just sit and must, justify all the steps, it will take you a few months, but you will end up with a solution. We wanted to get a cute solution, like as simple as possible, as elegant as possible. And we wanted to be sharp with this small n and capital N, which this maybe if you want something sharp, it requires a little bit more care. But I'm pretty sure that, I mean, we are not talking about breakthrough, I think the applications of this F capital N are much more spectacular. Like the things that I mentioned in the first talk, I'm much more happy about this progress. But yeah, I mean, we couldn't find in the literature the full arguments, and definitely there were much more partial arguments written very recently by people who know much more than I do about Bethe-Ansatz. So
I understand. Yeah. Thank you. Okay, maybe I'm also curious. So have you spoken about this particular work in front of an audience of physicists or not yet?
No. I have a fairly bad memory of a talk with Q larger than 4 in front of a physics audience.
Oh, really? So what did they say?
I'm not so much looking forward to it. Well, because they were, for instance, explaining that what was done so there were an argument by Baxter about to prove discontinuity.
Yeah.
But this argument was really based on 8-vertex model. And he also is absolutely clear. So there is no Bethe-Ansatz. He needs to justify it by this, I mean, he has another argument. And there he makes an assumption and he is very clear about it. Yeah. But the whole school that follows kind of forgets about the careful words of the master. And so I ended up fighting with people that were not thinking that. And in particular, I was trying to argue that we were not doing what Baxter was doing in the sense that we never went to 8-vertex model. We really stick with 6-vertex model and look at this, if you want, as a 6-vertex with different density. And that was the trick. And then, okay, the justification of the Bethe-Ansatz, maybe these people believe it was true. I'm okay with that.
Right.
But it's true that it was kind of a little bit violent. So I'm not especially looking forward for a
Well,
talk.
maybe you should travel to Australia and give a talk in front of Baxter.
Yeah, but
and then...
if you go actually, for instance, I was discussing with the gear, like the top people in the field, they definitely know their stuff. So I mean, when you pinpoint a place where you think that you need to justify something, they tell you, yes, it needs to be justified, and I don't know how to justify it. So it's more when you are far from Australia that things get messy. But Australia is a safe place. It's
Yeah.
Okay. Well, maybe we can all remotely go to Australia at some point. In the meanwhile, we'll stop. I'll at least get lunch. I'm going to close this session, and we'll start again in, I guess, about 23 minutes with Greta's third and final talk. So let's all thank Hugo again for a very nice.
Thank you very much.
Thank you. Thank you.
See you in a little.